You know, I was standing in my backyard this morning, just looking down at the grass.
Right.
And you have this feeling, we all do, instinctively, that the ground beneath us is, well, the definition of stability. It's a solid ground.
It's the one thing you're supposed to be able to count on. Literally the foundation of everything.
Exactly. But then I started reading the research for this deep dive, and honestly, it kind of gave me vertigo.
Oh, yeah.
Because if you zoom out, or I mean, if you zoom in way, way down, that stability is a total illusion. The ground isn't just dirt and rock.
It's more like a lid on top of a cauldron.
A cauldron, yes. It really changes your perspective. We're just, living our lives up here on the surface, completely unaware that the engine room downstairs is just churning away.
And not just churning, it's occupied, as you put it earlier.
That's the thing. We are talking about these massive continent-sized structures buried nearly 3,000 kilometers beneath our feet. Titanic structures, the study calls them.
And the really wild part isn't just that they exist, it's that they seem to be running the show.
Right. We think of things like, Pangaea breaking up or the magnetic field shifting, and we think of those as surface events or maybe core events.
But this research suggests there's a kind of middleman controlling it all.
So today, on the deep dive, we are unpacking a really groundbreaking study. It was published in Nature Geoscience, led by a team at the University of Liverpool.
And they used some seriously heavy-duty tech to figure this out. We're talking supercomputers, geodynamo simulations, global seismic data, basically every tool they have to peer into the center of the Earth.
And their whole mission was to solve this one mystery that's been bugging geologists for decades.
Which is, why is the Earth's magnetic field so weird?
Yeah, why isn't it this, perfect shape? And the answer seems to point back to these two giant anomalies in the basement.
The giants in the basement. I like that.
Me too. So let's start there. We've got these two massive blobs, but blob is my word. What is the technical term? What are we actually looking at?
So the technical term is a bit of a mouthful. Geologists call them LLSVPs.
LLSVPs.
Which stands for Large Low Shear Velocity Provinces.
It sounds like a bureaucratic agency inside the Earth or something.
It does, doesn't it? But the name is actually a pretty functional description of how we even found them in the first place. It's all based on seismic data.
From earthquakes.
Exactly. When a big earthquake happens, say, in Japan, it sends these energy waves ringing through the entire planet like a bell.
And we have sensors all over the world that are listening to those rings. It's kind of like a CT scan for the planet.
That's a perfect analogy. And what scientists noticed is that when these specific waves, they're called shear waves, travel through the deep Earth, they usually move at a consistent speed.
Okay.
But when they hit these two specific regions, one under Africa, one under the Pacific, they hit the brakes. They slow down a lot.
So that's the low shear velocity part.
That's it.
So if I'm picturing this, it's like a sprinter on a track, and then suddenly they hit a huge patch of deep mud.
Exactly. They have to slog through it. And because they slow down, we know the material there has to be fundamentally different from the rest of the mantle. It tells us it's denser and it's significantly hotter.
And when you say large, we're not talking about something the size of a city, are we?
Oh, no. Not even close. These things are colossal. We're talking about structures that are each roughly the size of the entire African continent.
Wow.
But they're buried 2,900 kilometers down, sitting right on the boundary between the rocky mantle and the molten core.
Just picture that. Two continent-sized mountains just sitting there in the dark under all that pressure.
But here's something that stuck out to me.
Yeah.
They aren't solid rocks, right? They're not like giant granite boulders.
No, and this is where you have to sort of let go of the solid rock idea. I mean, the mantle is solid rock, technically, but on geological timescale.
Millions of years.
Millions of years, exactly. It flows. It behaves more like an incredibly thick, viscous fluid, like silly putty or maybe asphalt on a really hot day.
So it's solid to us, but it's liquid to time. Precisely. So these LLSVPs, let's just call them the blobs to keep it simple. They are these distinct piles of material. They're chemically different, probably enriched in iron, and they are incredibly hot.
And the study points out that they're accessorized. They aren't just floating there. There's a whole architecture around them that I found fascinating.
Yes, and this is the really critical detail for the whole magnetic field connection. You have the hot, dense blob in the center, but surrounding it, kind of wrapping around the edges, is a ring of cooler mantle material.
A cool ring in the middle of the deep Earth.
Right. And in the seismic data, the waves actually speed up when they hit these rings, Fast waves mean cooler, stiffer material.
Okay, but where does a cool ring even come from down there? I'm assuming there's no air conditioning.
No air conditioning. It's actually,
Yeah.
it's the graveyard of the surface. Remember plate tectonics?
Sure.
Well, when one tectonic plate dives under another, that process is called subduction. That cold, dense ocean crust sinks. It doesn't just melt right away. It sinks all the way to the bottom of the mantle.
Wait, so you're saying the cool ring is basically the crushed up remains of ancient oceans?
Essentially, yes. It piles up around the edges of these hot blobs, almost like snow drifts against a wall. So you end up with this really sharp thermal contrast. A superheated pile in the middle and this cool wall of ancient slabs around the outside.
That is wild. The floor of the mantle is cluttered with the ceilings of the past.
That's a very poetic way to put it, yeah.
Okay, so we've got the hot blobs under Africa and the Pacific, and we've got these cool rings of dead oceans wrapped around them. But the Liverpool study says this specific setup is what's messing with our magnetic field.
Right. This is the crux of the paper.
But this is where I need you to bridge the gap for me, because I thought the magnetic field comes from the core, not the mantle. I mean, the mantle is rock, the core is metal. How does a rock blob upstairs tell the metal downstairs what to do?
That is the million-dollar question. And the answer is thermodynamics. It all comes down to heat flow.
Okay, break that down.
So you're absolutely right. The magnetic field is generated by the geodynamo, which is just the swirling movement of liquid iron in the outer core. But you have to ask, why does that iron move in the first place? What's powering the engine?
Heat, I'm guessing.
Heat, exactly. The core is incredibly hot, and it wants to get rid of that heat. It's trying to cool down by dumping it into the mantle above.
Okay.
That cooling process causes convection, hot iron rises, cools against the mantle, sinks back down, and swirls around. That swirling motion generates electricity, which creates the magnetic field.
So the flow of the iron, the speed and the direction is all driven by how fast it can lose heat to the mantle.
Precisely. Now imagine the mantle isn't a uniform blanket. It's like you're lying in bed. If you have a thin sheet over you, your body heat escapes easily. You feel cool.
Right.
But if you put a thick, heavy duvet on just one part of your body, say just your chest, that part gets really hot. The heat can't escape.
I see where you're going. The LLSVPs are the heavy duvet.
They are the heavy duvet, exactly. These blobs are already super hot, which means the temperature difference between the core and the blob is small. So the core can't dump heat into the blob very efficiently.
Like a lid.
It's a lid. It acts as an insulator, so the iron underneath the blob becomes sluggish. The flow just slows right down.
But then you've got the cool rings right next door.
The open windows.
Yeah.
Right. The cool rings are these cold ocean slabs. The temperature difference there is massive.
Yeah.
The core can just dump enormous amounts of heat into those cold regions. So the iron underneath the cool rings starts churning like crazy.
Wow. So you have this completely lopsided engine. Under the African and Pacific blobs, the flow is lazy, sluggish.
Yeah.
And under the cool rings, it's basically sprinting.
Exactly. And that inconsistency, that asymmetry, is what shapes the magnetic field. The study argues that the mantle is essentially dictating terms to the core. It's top-down control.
So the pattern of the magnetic field we see on the surface is a direct reflection of that hot and cold pattern 3,000 kilometers down.
That's the idea.
It's like the LLSVPs are traffic controllers. They're forcing the iron into specific lanes.
That's a great way to visualize it. They're absolutely steering the flow.
And this explains why our magnetic field isn't a perfect sphere, because I know if you look at a magnetic map of Earth, it's kind of wonky. Magnetic north wanders, the field strength varies.
Wonky is the perfect scientific term for it. If the mantle were perfectly uniform, just a smooth shell all the way around, the core would cool evenly. The magnetic field would be a perfect dipole, like a bar magnet. Very boring, very symmetrical.
But because of the blobs?
Because of the blobs, we get anomalies, we get tilts, we get weak spots. In fact, there's a famous weak spot called the South Atlantic Anomaly right over South America.
That's the one where satellites have issues when they fly through, right? They have to shut down instruments.
They do. They get blasted with more radiation because the shield is thinner there. And guess what the simulation showed is sitting directly underneath that anomaly.
Let me guess. The edge of the African blob.
The edge of the African LLSVP. The model showed that the specific flow patterns caused by that blob create these reversed magnetic flux patches. It basically creates a dent in the shield.
Which brings us to the proof part of this, because, I mean, obviously we can't go down there and stick a thermometer in the outer core.
No, that would be a challenge.
So how did the Liverpool team confirm this?
They turned to the most powerful tool we have for this: supercomputing. They built these massive simulations of the Earth's geodynamo.
I always love when we use silicon to solve, these ancient mysteries of stone.
It's really the only way. So they created two different versions of Earth in the simulation, a comparison test. In Earth A, they modeled the mantle as perfectly uniform, a smooth shell, same temperature everywhere.
So the perfect mirror.
A perfect model.
Yeah.
And they hit play, let the physics run for millions of simulated years, and the result was a magnetic field that was too perfect.
It didn't look like our Earth.
Not at all.
Yeah.
It was highly symmetrical, aligned perfectly, didn't match reality.
Okay, so then what about Earth B?
In Earth B, they programmed in the LLSVPs. They put the hot blobs under Africa and the Pacific and the cold rings around them, all based on the real seismic data we have. And the computer spat out a magnetic field that looked almost exactly like the one we observe today. It reproduced the tilts, the weird eccentricities, and crucially, those anomalies like the one in the South Atlantic.
That's the smoking gun.
It really is. It's the strongest evidence we have that the shape of our magnetic shield is being determined by these two giant structures. The math only works if the blobs are running the show.
But the study didn't just look at today. And this is where my mind really started to wander into, like, sci-fi territory, even though it's real science. They looked at the timeline.
Yes. They suggest this whole setup has been in place for at least 265 million years.
265 million. That takes us back before the dinosaurs, to the Permian period.
It takes us back to the time of Pangaea.
Yeah.
And this is where the implications just get enormous.
Yeah.
Because if these blobs have been down there that long, messing with the core, they've also been messing with the surface.
The source mentioned ancient continental configurations. Are we implying the blobs move the continents? I thought plates move because of things happening at the surface.
Well, it's a feedback loop. Remember those cool rings, the sinking slabs?
Yeah.
The position of those slabs is determined by where continents are crashing into each other on the surface. So the surface affects the deep Earth.
Okay, right.
But it works the other way, too. Many geologists believe the LLSVPs themselves are stable anchors, and that while the cool rings are sinking, the edges of the hot blobs are rising. They send up these huge plumes of hot rock.
Like a blowtorch from below.
Exactly like a blowtorch. And if you put a blowtorch under a supercontinent,
You break it.
you break it. There is a very strong theory, and this study supports it, that the breakup of Pangaea was actually driven by superplumes rising from the edges of the African LLSVP. It literally pushed Africa and South America apart.
So these things are continent killers.
Or continent creators. But yeah, the geometry of our world, where the continents are, which dictates ocean currents, global climate, where life evolves, it might all be dictated by the blobs.
The source also mentioned paleobiology. At first, that seems like a stretch. How does a blob 3,000 kilometers down affect the evolution of a lizard?
It all comes back to the shield. The magnetic field is our only real protection from solar wind and cosmic radiation. If the LLSVPs cause the field to become unstable or even trigger a reversal where north and south flip,
That weakens the shield for a while.
it weakens it temporarily. And a weaker shield means more radiation hits the surface, more UV, more cosmic rays. It can change atmospheric chemistry, damage the ozone layer, and lead to higher mutation rates in DNA.
So you have this chain reaction. The blob changes the heat flow.
The heat flow changes the magnetic field.
The magnetic field weakens, the radiation spikes, and suddenly life on the surface has a really, really bad day.
It's a bit dramatic, but that's the connection. There are these long periods in Earth's history where the field was unusually stable, and that seems to line up with the stability of these LLSVPs. When things shift down there, life on the surface feels it.
It just connects everything. I think that's what I'm taking away from this. We put things in boxes. Geology is rocks, biology is animals, physics is magnetism.
But you can't separate them. You really can't. The Earth is a single integrated system. The fluid dynamics of the core are coupled to the solid mechanics of the mantle, which is coupled to the atmosphere and the biosphere. It's all one machine.
It's humbling. I mean, we're just riding on the crest, completely at the mercy of the engine room.
We are, and we're only just now starting to get the blueprints to understand how that engine even works.
So let's try to summarize this. We went from standing in the backyard thinking the ground was solid.
To finding out it's a moving conveyor belt sitting on top of a cauldron.
Right. And deep inside that cauldron, there are two continent-sized, ultra-hot blobs, the LLSVPs, surrounded by rings of crushed ancient oceans.
And those temperature differences, the hot blobs and the cold rings, act like a weird thermal blanket.
forcing the liquid iron in the core to flow in these irregular, lopsided patterns.
Which creates the imperfect but absolute vital magnetic shield that protects us all.
And has likely been steering the movement of continents and maybe even the history of life for over 200 million years.
It is a lot to process, but it gives you a newfound respect for the ground beneath your feet. It feels a little less solid, but a lot more alive.
I want to leave you with one final thought. We talked about how these blobs might have influenced evolution, pushing continents apart, maybe letting radiation in during field reversals.
Sure.
Well, if these structures have been the traffic controllers of Earth for 265 million years, think about human history. Our migration out of Africa, the climates we adapted to, the very shielding that allowed our complex brains to evolve without being fried by cosmic rays.
That's a heavy thought.
How much of us, our history, our very existence, is actually being dictated by two hot, dense blobs of rock buried 3,000 kilometers down? Are we the main characters, or are we just living in the guest house of the LLSVPs?
I think we know the answer to that. We're definitely just the guests.
Something to think about the next time you check Google Maps. Thanks for diving in with us.
Keep exploring.